Alright, so let's have a look at some foundational concepts that you hopefully encountered in previous courses. First of all, we'll start off with kinematics. We'll do a two-dimensional example. We'll launch a projectile here at an angle of 30 degrees and with a launch velocity of 40 meters per second. Now, one of the concepts of elementary physics is that we have to resolve this into components and treat the two components separately, because in the x direction this will be the x velocity here, this adjacent side of the triangle, that's the initial x velocity. There's no acceleration in the x direction, and in the y direction, this will be the initial y velocity, this component here, there's an acceleration due to gravity. So we have to split these up, the x and y directions, and treat them separately. So this is the opposite side of the triangle. Sine 30 is Vy over 40. Cross multiplying, Vy is 40 sine of 30 degrees. That's 20 meters per second upwards. The x velocity is the adjacent side, so cos 30 is Vx over 40. Cross multiplying, Vx is 40 cos of 30 degrees. And that works out to 34.64 meters per second. So at this point, I like to make a chart where I separate out the x and y motions, like a t-chart here. There we go. And so if we consider the y motion over here and the x motion here, now we're asked to find the flight time and range. The way to find the flight time is first of all to find the rising time up to the top, because up at the top here, although it doesn't stop, it's still moving to the left, the y velocity stops. So it's no longer going up or down. So we can find the rising time using a kinematics equation. So this is the velocity equation when you're accelerating. Final velocity is initial velocity plus at. You can do vi or vo. So using the y components, the final y velocity is 0 at the top. The initial y velocity is 20. The acceleration in the y direction is downwards 9.8, and the rising time is unknown. So solving this for t, bring the 9.8t over and then divide. So now just divide both sides by 9.8, we get the rising time. Now then for the total flight time, because rising and falling is symmetric, we just double that. So to get the total flight time, it's just 4.08 seconds. Now that we've got that, we can come back and analyze the horizontal motion. In the horizontal direction, there's no acceleration. So we can find the displacement using the displacement equation. D is vit plus half at squared. There is no acceleration, so this whole term disappears. So the initial x velocity is this 34.64, and then the time is the flight time is the 4.08 seconds, and then this whole term here is 0. So this means that our projectile went 140.14 meters, which is about 400 feet. So that would be pretty good if you were a golfer. Now, we're also asked to sketch some graphs here. So we'll start with velocity graphs. So these are just visual representations that show us how the velocity changes with time. So this will be for the x, and this will be for the y velocity here. That didn't work out well. So for the x velocity, if we think about it, we said there's no acceleration. So that means the x velocity is just a constant. It's a constant 34.5 meters per second. That's supposed to be a horizontal line. The y velocity is a little more complicated. Here, I'll use the line tool for this one. For the y velocity, it starts at 20 upwards, and then it decreases to 0 as we rise, and then it actually goes negative as the object is falling. And since rising and falling are symmetric, right here, so this is the 2.04 seconds, and right here, this will be the 4.08 8 seconds on the time axis. That's when it hits the ground. So at that point, the velocity very quickly is going to become 0 and just be along the axis there. So this is the time, the impact time with the ground. So this is rising, reaching the top. This is falling, hitting the ground and stopping. For graphs of displacement versus time, well, in the x direction again, if we're graphing displacement, we know that, or we perhaps remember that velocity is the rate of change, or the slope of the displacement graph. Now, since the velocity is uniform, that means the displacement is just going to increase uniformly with time. So that's a straight line. In the y direction, because of the acceleration, the y displacement is actually going to be a curved or parabolic graph versus time. So initially the y displacement is 0, so this is dy versus time. And so our displacement from the origin is going to, from the ground, is going to increase as it rises. It's going to reach the top right there. I should try and line these up a little bit. Let me do a better job there. Come on, eraser. There you are. So I'm just trying to line up my distance and velocity graphs here. There we go. Okay, so now I'll move this over, because what I'm trying to say is right here is where it reaches the top. Maybe I'll just put a little dashed line there for clarity. Oh my goodness, this is slow. Why has this become so slow? There we go. That's all I want. Just a little dashed line right there. And of course, it's not in the right spot. Oh my goodness. Now it's in the right spot. Heavens. Oh my heavens. All right, so there it reaches the top. So the y velocity is 0 at that point. And the y displacement is a maximum. And then it falls back down to the ground, reaching the ground right there at the same 4.08 seconds. So there's a review problem in projectile motion and also the graphical representation of motion. And this would be a typical problem you would do in Physics 12. Now, our intent here in this very quick overview is not that you should master these, but instead that you should be reminded of how you've done these problems in the past, and with a bit more practice, hopefully you are back at the mastery level. So that's a kinematics problem. Next, let's do a force problem. So we're going to pull a mass up a ramp. And you may recall the first thing to do is to draw a force diagram. Let's use some colors that'll stand out here. Okay, so what forces act on the block? Well, we're pulling it up the ramp, so there's our pull force. Gravity acts on this block straight down towards the center of the Earth. The surface is going to push on the object perpendicular to the surface. That's called a normal force. Normal means 90 degrees. And then because the surface is rough and the mass is being pulled up, there will be a friction force that is opposite to the upwards pull, upwards slide, so that'll just be downwards here. So there's friction. So those are the four forces that act on the object. Let's just label those. There's pulling force, normal force, friction force, and force of gravity, which is the weight, which is mg. And because this is a 10 kilogram block, this is 10 times 9.8, so that's 98 newtons of weight. Now you may recall that the next thing to do in these problems is to resolve gravity into components. We're going to set up a coordinate system here where the y direction is perpendicular to the ramp and the x direction is parallel to the ramp. So with those coordinates, we want to find a y component of gravity, so that's in this direction, so that's squeezing the mass onto the ramp, and then we want to find the x component that's pulling down the ramp, because gravity partly pulls down. Now, this is sometimes called the FGY and the FGX. I call this one squeeze and this one slide. Notice that these are two sides of a triangle where this is the hypotenuse of the triangle. And you may recall this ramp, we're told, is at a 10-degree angle. You may recall the really simple geometry to prove that this is also 10 degrees. So the angle here is always the same as the ramp angle. If not, the proof is simple. This is 10, so this up here must be 80, so this here must be 10. All right, so we resolve gravity into its components. The y component, so this is my x-axis, this is my y-axis. So the y component of gravity that I sometimes call the squeeze component, that's going to be 98 cos of 10 degrees. It's the adjacent side, and that we can work out is 96.51 newtons. The component of gravity pulling us down the ramp, that's going to be 98 sine of 10 degrees. That is calculated at 17.01 newtons. All right, so again, we analyze the components. We analyze force components in both the x and y direction. So x forces, y forces. Now, in the y direction, the mass doesn't move. It doesn't lift up off the ramp. It moves in the x direction. So what does that mean? Well, it means that when we sum the y forces to get the net y force, so this is one way to write net y force. You might just also write F net. That's the net y force. And this is just the sort of standard math symbol. It's sigma for summation. Now, we know that net force always equals mass times acceleration, right? So what is the net y force? Well, we've got Fn in the positive y direction. And then in the negative y direction, we've got this slide component. So minus the mg cosine theta component, cosine 10 degrees. And that's going to equal the mass times the y acceleration. But we already said the y acceleration was 0. So we know that Fn, the normal force, well, it's just going to equal 96.51 newtons. Now that's important because in the x direction we know that friction depends on the normal force. Friction depends on the surfaces in contact, and that's the mu constant, which is given as 0.1, and it depends on how much force is pushing the two surfaces together. That's reflected in the normal force. So we have about 9.65 newtons of friction here. Now we're going to consider the horizontal motion. We know we're pulling it up the ramp with this applied force. We could see that this applied force and friction are opposite. So when we sum the x forces, we're going to have positive direction pulling force, negative direction friction. That's going to equal ma. That's the acceleration in the x direction, which is the only acceleration. So this is called a net force equation. Now, oh, I missed one. Oh my goodness me. Because there's actually a third force we need to remember here. Okay, not only do we have this force up the ramp and this force down the ramp, we also have, of course, our component of gravity that's acting down the ramp as well. Now, I put it down here to make the triangle nice and easy to draw, but we got to remember that it is actually pulling the mass down the ramp. So here I've got to subtract off, or I say in the negative direction, we also have mg sine of theta. Alrighty, so now we can ignore that email, and we can substitute in. The pull force was 55. We had 9.65 newtons of friction. We had 17.01 newtons of gravity pulling us down the ramp. That's going to equal mass times acceleration, and we could just solve directly for the acceleration. So this example is then complete now, and it shows us a couple of things. It reminds us of net force equations. It reminds us of ramp analysis, how we resolve gravity into its components, and it also shows us force diagrams and all sorts of things like that. So this is a really good review problem. Now, when we get to class, I'll do another example of each of these sorts of problems, and then you'll work on some in teams, and then we'll have a quiz, and that's kind of how the course will proceed. Before we leave forces, we should just talk about two types of friction. Now, you may have heard this idea before, but we know that friction opposes motion. And in the last problem, the object was sliding. That's a type of friction that we call kinetic friction. Now, you actually can get friction on an object that's not moving, and that's called static friction. For instance, if you push on your desk a little bit, then it won't slide. If you keep pushing and pushing and pushing, eventually you'll reach the point where it's going to break free. It's not moving yet, but it's about to. We call that maximum static friction. And the amount of static friction is still mu times the normal force. But the mu in this case is the static coefficient of friction. And that static coefficient of friction is going to start at 0 if you're not pushing on the object at all, and then increase to some maximum value. Now, typically that static maximum value is bigger than the kinetic friction, because as soon as you break free and start sliding, well, it takes a little bit less force, doesn't it? So let's just do an example of this here. Really simple example. It's almost like a Physics 11 example. So we've got an object on a surface and we're pulling it. It's a flat surface. So the forces that act on the object are the Earth pulling down. Oh my. The Earth pulls down. Then the surface pushes up. That's called the normal force. Then we're pulling it. I guess we'll put the pull in this direction. And then there's friction. So those are the forces on the object. Fn, Fg is the weight, pulling force F, and friction here. We'll put our y-axis in this direction and our x-axis this way. So now we go about, and again, I find a t-chart a helpful thing to organize our work. We say, okay, x force is here, y force is here. Some of the forces in the y direction, well, you've got upwards normal force, downwards weight. It's going to sum to 0 because the y acceleration here is 0. So the y forces are just balanced. Now that's important because once we know the normal force, we can calculate the friction. Now there's two types of friction. There's this what we call the kinetic friction if you're already sliding, and that's given by the kinetic coefficient times Fn, and the kinetic coefficient was given here as 0.27. And the normal force, well, it's 10 kilogram object, so this is just 98 newtons of weight, and therefore 98 newtons of normal force. So the kinetic friction there, debuts at 26.546 newtons, or let's say 26.5 newtons. We also have this other type of friction, which is static friction, that will reach a maximum value and that maximum, the coefficient was given as, what was it, 0.35. Multiply by the normal force of 98 newtons, and we get 34.35 newtons of maximum static friction. Okay, now that's important because when we go to analyze the x forces, well, first of all, we'll write a sum of the force equation. So sum of the forces in the x direction. We've got our applied force in the positive direction and friction opposite to that. That's going to equal the mass times the x acceleration. Now, we have to be pulling with more than this maximum static friction in order to move. So if the force does not exceed 34.35 newtons, you won't move. So in problem A, where we're told the pulling force is 30, we know it's not moving. There's no motion at all. It's static. So that means that the acceleration is 0, and if you put an acceleration of 0 on this side, that tells us that the actual static friction required to balance a 30 Newton push force is actually 30 Newtons. So I'll call it actual, just to distinguish from the maximum. So because the acceleration on this side is 0, you could solve that and say, okay, if you're pushing with 30, static friction is going to exactly balance your pushing force. It'll push back with 30. Part B of this example, we're told that we're pushing with 50 newtons of applied force. So that's going to overcome static friction. We're now going to be kinetic. So now when we substitute in, so it's our 30 newtons of applied force minus our 26.5 newtons of kinetic friction. And that will equal our mass times our unknown acceleration, and we can actually solve for that acceleration. Now, oh sorry, it's not 30 here, is it? It's a 50 Newton push force. Silly me. Here, I'll just put it in green so it really stands out. Yep. Okay, so it's 50 newtons of pushing force for part B. And so solving for the acceleration, we get 2.35 meters per second squared of acceleration. So this example illustrates the difference between static and kinetic friction and some considerations that you have to make in analyzing static friction problems. Okay, there's a couple of more foundational concepts that we're going to go through. The next one is a related dynamics question. It's circular motion. So let's think about some key concepts of circular motion. So key thing to remember about an object in circular motion is that even if the speed is constant, as the object moves around the circle, the velocity is changing because this vector and this vector are different. So because the direction changes, that makes the vectors different, and that means there's a velocity change, and that means there's an acceleration. Now it turns out that the direction of the acceleration is inwards towards the center of the circle, as indicated on this graphic, and it has magnitude v squared over r. This should be familiar to you from previous physics classes. Now, if the object is traveling at constant speed around the circle, then we can say that its speed must equal distance over time. Now, the distance for a full lap is called the circumference, and the time for a full lap is called the period. Circumference of a circle is 2 pi r, and for period we use a special time, we use capital T. Now, we've said the acceleration must be inwards. If the acceleration's inwards, then so is the net force by Newton's second law. Those have to be in the same direction. So the simplest circular motion problem is just take a battery-powered car and hold it with a string, and then it'll go around in a circle. So this is in side view. If you looked at it in top view, so here's the post, or you holding onto the car, here's the string, and here's the little toy car with its 4 wheels going around in a circle like that. So, if we consider the dynamics of this situation, then what forces act on the car? Well, there'll be a tension force from the string, there will be weight, the earth pulling down, and there will be normal force, the floor pushing up. That's a horrible force diagram. Okay, there we go. That's a little better. Okay, so this is force of tension. This is force normal. This is force gravity. Now for our coordinate system, we're going to call the upwards direction y. That makes a lot of sense. And then this other direction here, I'm not going to call it x. I'm going to call it the inwards direction. Because in circular motion, that's the direction that matters. So if we sum y forces to start with, then we've got normal force in the positive direction and gravity in the negative direction. And we've got a car that's not going up or down, so there's no y acceleration. In other words, normal force balances weight in this case. If we consider inwards forces, then the only inwards force is the tension force, and so that's got to equal the mass times the inwards acceleration. Now, some books will call the inwards direction the c direction, but I don't like to use that there. Now, we saw on the previous page that that inwards acceleration had magnitude v squared over r, and so this then completes the force equations for this problem. We're asked to actually find the tension. We're given the length of the string, that'll be the radius, we know the mass, we know the speed, so we can plug and chug. So the mass is 1.5 kilograms, the speed is 2 meters per second, and the length of the string, which will be the radius in the circle, is 0.3 meters. That gives us a tension force of 20 newtons. Okay, so circular motion analysis was another important concept from Physics 12. A final concept from Physics 11 and 12 is energy and momentum. So momentum applies to collisions in a closed system, and so typically you'd have two things smashing into each other, and momentum is the product of mass and velocity, and what we find is that if you have a closed system, then momentum gets transferred between the objects from one to the other, but none of it gets gained or lost. So the momentum at the beginning and the momentum at the end for the system is the same. So here we've got one thing sliding towards another, so there's going to be an initial amount of momentum there. And then this is the after picture. And so there's a final amount of momentum here. And the law of conservation just tells us that it's got to be the same. So all the momentum at the beginning has got to equal all the momentum at the end. Momentum, you may recall, is the product of mass and velocity. So we can write this equation in an expanded way for a two-object system. M1 V1 initial plus M2 V2 initial will equal M1 V1 final plus M2 V2 final. So a really simple example, just a curling rock sliding and hitting another curling rock. So these both have a mass of 19.5. This one's moving at 4 meters per second. This one initially is at rest, so this is our before picture. After, so this same curling rock is now going at 1.5 meters per second. We just want to know how fast this one's going. Okay, so the total initial momentum will equal the total final momentum because this is a closed system, meaning the only forces from the outside world cancel each other out. Weight and normal force cancel each other out. So the only thing that's left is the collision force between the two objects, and that transfers momentum but doesn't allow any of it to be lost. So total initial momentum, so we'll have 19.5 kilograms here, moving at 4 meters per second, and then zero momentum for this other object. On the final side, that 19.5 kilograms moving at 1.5, and now we'll introduce an unknown plus 19.5 V. So 19.5 times 4, that's going to be 78. Then you subtract 19.5 times 1.5, and then you divide by 19.5. The result is 2.5 meters per second. Let's just do that here. So 19.5 times 4 minus 19.5 times 1.5, and then we divide that by 19.5. So that's the final velocity of that second curling rock, the fine Canadian sport of curling. Now, we're also asked about the energy in this collision. Now, mechanical energy is the sum of kinetic and potential energy. In this case, there's no potential energy to worry about, so it's just kinetic energy. And there's something known as the work energy theorem, and sort of more on this later in the course, but it tells us that if you have a non-conservative system, if there's a loss of mechanical energy, then this relationship applies. So the initial mechanical energy is just the kinetic energy of this object, so it's a half m1 v1 squared. And this is the work that's done in the collision that goes into deforming the objects, or it's also the heat created in the collision. Now the final energy here is again just kinetic, and it's the kinetic energy of the two objects added together. So initially we had this one going at 4 meters per second, and we're just substituting in the speeds which were given above, and now we're going to substitute in the V2 final that we just found from our momentum calculation. I'm just going to cheat by sliding this over a bit to give myself a tiny bit more room. There we go. And so we substitute that in to 0.5 squared, and now we can calculate W, which is the amount of mechanical energy that was lost. So it was either used to do work, deforming the objects, or it was transformed into heat energy. All right, and there it is. So the collision problem and the conservation of momentum and the mechanical energy principle were things you likely encountered in Physics 11 and Physics 12, and they're important concepts that we will be using in this course, but I just want to remind you of them here at the beginning. So in class, we'll work on some more problems related to these concepts and hopefully bring you back up to speed on them.